So Joomy, the stage is yours. Thank you.
Okay, thank you. Hi, everyone. I'm Joomy. I'm a researcher at Bloomberg's CTO Infrastructure and Security Research Team in New York City. Today, I'm going to present to you a proof pearl about game trees, implementing game trees as rows trees in functional languages, particularly Rocq, the proof assistant, and more importantly, recursively building game trees correctly. So let's start with the very basics. What are game trees? What are they good for? Game trees are mathematical abstraction in game theory. They're used to reason about games and searching for the best move in a game. Famously, Deep Blue, a program that did game tree search for chess, won against Kasparov in the 90s. Game trees can also be used for pathfinding and constraint satisfaction. Game trees concretely depict the state space of a game. A game tree consists of games, states of a game organized as a tree, where each branch leads to a state after one move. So let's see an example. Consider tic-tac-toe. We want to explore the state space of tic-tac-toe. The tree has the empty board at the root, as you see. And now player one has to mark X in one of the 9 empty cells. That means there are 9 possible moves they can make, and that there should be 9 branches of this root. So after the first move, this is what the game tree looks like. Now, at each of these new boards, we know it's the second player's turn. And in their turn, player 2 will have to mark O in one of the empty cells. And given that player 2 has 8 empty moves at each of these new boards, these new boards must each have 8 branches. I don't have enough room here to show the entire tree, so here's only the leftmost branch expanded. At each of these new boards, it's player 1's turn again, and the game keeps going. So I think you get the idea. The entire tree, assuming that we stop expanding a branch after a game is won, is around 550,000 nodes. So that probably wouldn't be the basis of our time here. So I'm going to get back to programming. There are various data structures we can use to represent game trees, but the most idiomatic and common one from functional programming languages is rows trees. So for those unfamiliar, a rows tree is a tree data structure in which a node contains a list of subtrees, as opposed to only 2 subtrees like in a binary tree. So here in the slide, we see definition of rows trees in Rocq. First, we have definition of lists, linked lists. We can either be nil, empty list, or cons, something that contains one element and another sublist. And after that, we have the type of trees. So in our definition, a rows tree can only be a node that has a root element and a list of subtrees. So this is the game tree for tic-tac-toe that we saw before, but now written as a rows tree. And obviously, we can write it out by hand like this, but can we write a function that builds this tree for us? So let's try. We want to make our function parametric over different types of game states. That is a type A here. Then we have the next parameter, a function that takes a state and gives us the list of states that are one move away from that. And then we have the init parameter, the initial state of the game. So I should be able to compute the entire state space from this, right? Well, let's attempt writing this function. The first solution here is to put the initial state in the nodes and then get the states after one move from the initial node by calling next, and then mapping over those next states with recursive calls. So great, we must be done. Just to make sure, let's check what Rocq says. Oh no, Rocq is not okay with this function definition. It says it cannot guess the decreasing argument of fix. Well, what does that mean? It means Rocq is not convinced that this function terminates. Rocq's termination checker often stops you when a recursive function is not obviously terminating. So what do we have to do to convince Rocq? Well, I do have to interrupt this line of thinking and ask, does this even necessarily terminate? For tic-tac-toe, sure, it will. But what about other games? Not all games are finite like tic-tac-toe. So if we're trying to explore the state space of an infinite game, then the game tree will not be finite. And that's a bit of a problem for us, because we define rows trees in Rocq with inductive data types. Inductive values are finite, and recursive functions in Rocq must terminate. Where does that leave us? Now we have 2 problems that we need to deal with. 1, how do we write the recursive function that we wanted to write? And 2, how do we represent and compute infinite trees, especially if we want to deal with infinite games? And there's a way we can answer both of these questions, and that is coinductive types. With inductive types and recursive functions, we could only have finite values and terminating functions. With coinductive types and co-recursive functions, we have possibly infinite values and possibly non-terminating functions. So let's look at our failed attempts of writing unfold for inductive trees and make it work on coinductive trees. And yeah, if you just add code to a lot of stuff, that works just fine. And those of you who have dealt with coinductive values and tried to reason about them before might say, but Joomy, we could have had a finite tree and it would be a lot easier to write proofs about them. Do not worry. Even if we have a possibly infinite code tree, we can still convert that to a finite tree by taking a finite number of elements from the code tree. This is what the proof assistant folks call the fuel pattern. We have a program that may or may not terminate, so we add a fuel parameter and let the program run as long as there is some fuel. And now using the function to convert a code tree to a tree, we can say a tree is finite if at some point adding more fuel doesn't change the tree that you get. And using that definition, we can even say a game, as defined by its initial states and next states function, is finite if the unfolded game tree is finite. And using that, we can prove that tic-tac-toe is a finite game. We need to unroll the tree, a game tree 10 times, hence they exist 10. And 10 because 1 for the empty board, and 9 because the longest game of tic-tac-toe takes 9 moves, so that's 10 times. So what are the lessons to learn from here? The first one is coinductive types can be infinite, so they don't require termination checking. They require productivity, but that's a different story. And with no termination checker, writing unfold gets a lot easier. Lessons that we don't really have the time for today, but are in the paper, is reasoning about coinductive values is much harder and more verbose. Our proofs about coinductives take about twice as long as our proofs for inductives. And reuse of coinductive proofs in Rocq is annoying, but one can get around it. There are a bunch of methods that we mention in the paper, but we don't actually use them. But for some kinds of reasoning, you also need techniques like bisimulation, which we also explain in the paper. So let's get back to inductive game trees. I believe we can still rescue this function that we had before. So we had a function that we, 1, could not convince Rocq that it's terminating, and 2, actually does not terminate for infinite games. So let's write a version that works for finite games. Here's an attempt. This is very similar to the version that we had before, except now we have a relation R, and our next function returns new game states that are less than the previous states according to that relation. Except that's not enough to convince Rocq. We need to prove that this relation is well-founded, and then use the well-foundedness of this relation to convince Rocq that this function terminates. What I mean by well-foundedness, I mean that things should not be able to keep getting smaller forever. In other words, it's impossible to have an infinite decreasing chain. So take the less than relation on natural numbers. You cannot build an infinite decreasing chain because you cannot get smaller than 0. So less than on natural numbers is well-founded. Or take the strict subset relation on sets. There is no strict subset of an empty set, so no infinite chain. And now we have a game state type A and possible game states of that type, A1, A2, and such. We don't know yet that the relation R in game states is well-founded, so we need to prove that. I won't show you how to write that spec or how to prove that. The constructor formulation is a bit different than the one that I present here. So, but I will show you how to use that proof to do general recursion. We will use it by breaking our unfold function in half into an entry point function and an auxiliary function. So here we have the entry point function that requires the relation R to be well-founded, and then uses that well-foundedness to generate an accessibility proof. We also have an auxiliary function that takes that accessibility proof and uses it to perform recursion. I'm not going to show the definition of accessibility here today, but you can think of it this way. As long as we have a value that is less than what we started with, we can use that value in a recursive call. And since there can be no infinite descending chain in this relation, then the function has to terminate. This idea is the essence of all methods to perform general recursion like this in Rocq. Methods like program fixed point, equations, they all use accessibility under the hood. And thanks to this, we now have an unfold function for inductive game trees as well. But whenever we want to use them for a game, we have to define a relation on game states for that game and prove that the relation that describes the moves of this game is well-founded. So what are lessons to learn from this? General recursion on inductive types is well understood. but it can be a bit labor intensive because you have to prove the well-foundedness. Lessons that we don't really have time for today, but are in the paper, is that getting around the termination checker can require carrying around extra bits of proof, which forces us to make our verification more intrinsic. So we gotta interleave the proof and the computation a little more, just so that we can satisfy the accessibility predicate. So a question you might ask is, how do we know that we're generating the right trees? So to answer this question, we have a notion of soundness and completeness for unfolding. What I mean by soundness, I mean that if there's a game state in the unfolded tree, then there must be a sequence of moves from the initial state to that state. And what I mean by completeness, I mean that if there's a sequence of moves from the initial state to a state, then that state must be in the unfolded tree. So we prove this, both soundness and completeness for both inductive and coinductive trees. And this is what the theorem statements for them look like in Rocq. In both, we say that a game tree is in the unfolded game tree if and only if there's a sequence of moves, in other words, a path from the initial state to that state. In the paper, I talk about useful tricks for proving these theorems in Rocq and how to avoid certain pitfalls. Also in the paper, we show example applications of unfolding game trees. The first example that we present is a tic-tac-toe game with an unbeatable AI, thanks to the game tree that we build through unfolding. Second example that we show in the paper is a very primitive SAT solver that tries to find a model for a formula by trying both true and false for every variable, so essentially brute forcing it. Once we prove that such an assignment actually decreases the number of free variables in a formula, then we can fold that tree and find a set of assignments that make the formula true, and that is all we need to have a SAT solver. In the paper, we also discuss we have a short discussion of efficiency concerns and more clever search methods over the game trees that we built. So I want to end the talk with another possible application. Since this is mostly a PL audience, imagine evaluating lambda calculus terms as a game, where your initial state is the expression you want to evaluate, and reductions are the moves in this game. So for lambda calculus, this is going to be an infinite game, because you can have infinite sequences of reductions. So you will want coinductive game trees. But if we were talking about same type lambda calculus, SDLC, we may have wanted to use inductive game trees because we know SDLC is strongly normalizing. However, to unfold the inductive game tree, you would have to provide a well-foundedness proof, a well-founded relation, and that is equivalent to the strong normalization proof. Well, why might you want to reason about lambda calculi with game trees? Game trees let you look at different paths of evaluation at the same time. And if your next states function contains all possible reductions, you can then reason about what reductions are possible and what are not possible at the same time. Thanks so much for listening. If anyone's interested, the repo of the Rocq proofs is open sourced. Check out the Bloomberg organization on GitHub. Thanks.
So I don't know if you will hear the question. In case you don't, Joomy, just tell me and I will repeat it.
Okay.
Thanks for the talk.
Okay.
Can you hear me?
I can barely hear, but it's a bit unclear. I may ask for repetition if I don't understand, but okay. Please go ahead.
Okay. So my question is, when you moved from inductives to coinductives, you did two generalizations at the same time. So you made your trees possibly infinitely deep, but also possibly infinitely branching. But for all examples, yes, you only used finitely branching games, as far as I saw.
That's correct, yeah.
Could you have gone only halfway, so only made the trees coinductive but left the lists inductive?
Yes, I could have. In fact, the first iteration of this paper did that. And then I found that it's an easier presentation if I make both coinductive. But also, you know, if I'm claiming to support infinite game trees, I better be able to cover all kinds of infinite game trees, not just horizontally infinite or vertically infinite. But yeah, you're right that I should have had an example. Just you have limited space on a paper, so this seemed like an easier presentation.
Hi. So thank you for the great talk. When you start talking about accessibility predicates, you have to have this little distribute function over the next of init, so as to, well, copy the proof along with each element so that you can recurse on them. How does that impact running this code? That is, when you extract, you end up mapping the identity function over every element at every level?
Believe it or not, it's optimized away by OCaml extraction.
Any other question? Then, if not, let's thank the speaker again.